What is going on, everybody, and welcome back to the Unconventional Neural Network series. In this video, what we're going to be doing is running over some of the results from the neural network that was trained just to do addition. We're going to talk about some statistics. We're going to see how it did, and then what we're going to be looking to do moving forward. So with that, let's hop in. First of all, how did we do? So one thing I did was I wrote a few different kind of scripts just for comparing how we're doing as time went on. So one thing we can do is inside model we should have the train log directory. So one option we have is to just do cmd here and then just do python tensorboard logdir equals train underscore log. Run that. And then we want to open this, so let me just pull that up over here. So these are the results. So we can obviously see how loss was doing. So actually this model could have continued to train well. Oh, actually, I'm sorry. This probably isn't fully loaded yet. We probably need to wait a minute. Yeah, so you can see it's slowly starting to level out. We'll kind of need to wait for that to finish processing. So one way that we can see how a model's doing is to look at train log, but part of the issue is with loss, the loss is really all about the weights. And when we're looking at something like a mathematic problem, or in our case, like when we're doing the NMT chatbot even, there's a reason why we used other metrics like BLEU and PPL, because loss could mean, sure, we're learning something, but are we learning the thing we were hoping to learn? That might be a different question, so you often want to come up with a separate metric for that. So what I did was just manually, as this model trained, I just took the output dev as they came through, and I just renamed them quickly. So as they were coming, I would just say at what step point was that dev. So at 5K steps, 10K steps, and so on, all the way to 257K when it finished training. After about 100K, I just went to bed. So that's why I didn't get anything in between there. Hopefully our tensor board is done now, so we can kind of pull that up. And I'm just going to refresh it. So let's just open up loss. Okay, so so we can actually see after about 120K steps, it looks like I'm going to guess that the learning rate was taken down there as well. Let's see, at 120. Oh, actually, yeah, so right before I went to bed, I recognized that the learning rate was 1e negative 5, or it should have been 1e negative 5. Yeah, I wonder why that says 1e negative 4. Weird. Oh, this is negative 1e negative 4, so the middle ground here is 1e negative 5. Okay. Anyway, before I went to bed, that was going to be the last epoch, and I thought it was still only about 50% accurate. So I decided, you know what, let's add some more epochs, and when I did that, it jumped back up. So interestingly enough, we were actually kind of done learning. Then I allowed it to jump back up, and look how we just, boom, we just jumped way down in loss. So if anything, looking back, this is actually the first time I'm looking at this, that jump up in learning rate, basically what that tells me is we jumped down way too early. We shouldn't have jumped down that early. Because putting it back up, like we were fixing a plateau right there, basically, but allowing it to jump back up again comes back down here, and that's probably what sealed the deal. So, cool. I'll keep that in mind because we're going to make things a little more complex here. So, cool. So that's the tensor board, but that doesn't tell us, learning rate doesn't tell us did it actually learn math. So instead, what I used was the output dev file. So just open one of those up. Let's do Sublime Text, and we can see, okay, that's basically the output from the model. And it's because it's a character level model, the spaces aren't actually spaces, it's just spaces between the outputs. Now the input to these was basically it would be like new data and then from. So from this, we should get this. Is that correct? That's probably correct. Anyway, 169. Yeah. All right, so yeah, from here, we should get this, obviously minus the spaces. And the question is this correct or is it incorrect? Now, even at 5,000 steps, I know that this is probably about, I know it's about correct because they're at least close. They're within the same range, the same ballpark, right? But not all these are correct. So what I did was I just kind of manually saved those output devs as they go. So those were that's like our way of validating things. So every 5,000 steps, or about 5,000 steps, it would go to these testing ones, which contain samples so they're out of sample testing from like the training data itself. So these should be samples that the model has never seen, and this is how it does on those. So what I did was I at least started with this file. So let me open that up and we'll talk about that. So this one opens dev 10K, but we can start with 5K even. And what it's going to do is it's going to open up the test file, so test from. It's going to open up the output file, and then it's going to open up test.2. So what was it supposed to be? And then what we're going to do is just create a couple of counters here. We're going to follow pep8. Ooh, we should put our spaces here. Okay. And here too. Anyway, what we're going to do is we're going to count basically how often were we correct versus how many total samples did we have in the set. And then we can get an actual accuracy rating. So that was like the first thing I started doing. Man, I got a lot of pep8 issues here. Every now and a while, someone says my code is ugly. And I say, you're banned from the channel. So let's go ahead and run this. So as we can see here, basically what the output of this is what the input was, what our desired output was, and what the model said, hey, this is the output of like this, like the output of 43.8 thousand plus 98.8 basically. It should have been 142,000 and some change, and we said 144. So actually almost immediately we can see, hey, this model is at least on the right track. But at this stage in the game, to me, I'm starting to think, is it only getting close because it's basically brute forcing this and it's finding another example where it was close to 43,808 plus something close to 98,000 because we've got millions of samples. Is it just getting close because it's just like putting the output of what that was back in that example? And so at least my line of thinking here is one, that could be the case so long as accuracy, actual accuracy doesn't improve. That's one symptom of maybe it's just brute force. The other symptom of brute force is doing something like we're going to do later, which would be tracking the total absolute difference of the model out versus the desired out. So not only should accuracy be rising over time, but the total difference between accuracy and what we intended, kind of like loss, only this is much more exact to our task. We'd like to see that going down as well over time. And if that starts going down over time, we can be relatively comfortable that, no, it's actually seeming to learn some sort of math here. And then, of course, at the final stage of the game, if it is able to get any accuracy, so the 0.0 means it got none of them right. If it's able to learn any accuracy and that starts going up, then we're to assume that it's learned math. And my argument further is that we had 100,000. So it's 0 to 100,000 plus 0 to 100,000. So that's 100,000 combos here, 100,000 combos here. To get the total number of combinations on both sides of that plus sign, that would be 100,000 times 100,000, which should come out to 10 billion possible combinations. Now the output isn't 10 billion possible combinations of output, but as far as input's concerned, that's 10 billion, and we only fed through, I think, 3 million. So someone can feel free to correct me. Sometimes I get these kinds of scales wrong and stuff like that, but to my understanding, like, you could have 0 to 100,000 here, so that's 100,000, and then even here, you've got 5, and then you've got 100,000 examples of 5 plus what? So 100,000 times 100,000, 10 billion. So it can't, in my mind, be brute force either there. But it is simple math. It's just addition. Okay, let's see how we did later on. So that was 5K. How about at, I don't remember, I think I had a 15K. Let's just test it real quick. So even at 15K, we got some yays in there, and it's 1.2%. You might be asking, how's it 1.2? We have 500 samples, so that's why. So anyways, we have suddenly we're making some accuracy. Now, like I was saying, the other thing that you might want to start doing is tracking the total difference. Let's see if I'm doing that in this one. So in this one, we start tracking not only the total accuracy, but also the total difference. So starting from, let's just do 5K and then we'll jump to 25K. At 5K, the total difference, so think of it, again, it's just like the loss. The total is almost 400,000. But by the time we jump to model after 25K steps, the total loss or the total difference, I'm calling it loss, but because that's kind of what it is in my mind for this exact problem. It's not loss. Anyway, the total difference that it was off was only 21,000. That's a massive improvement after just 20,000 steps. Now I know everybody's waiting for the final result. So let me open up comparing number 3. And basically what I did here is rather than printing the actual desired out and the model out, I'm just running through, well, where did it go? Oh, I opened it in idle. I'm so used to using idle. Let's open it in Sublime. So in this one, I just iterate over, I was really mad, but I iterate over all of the checkpoints that we have so we can kind of see how it does over time. So, my apologies, I just have to fix it. And then pretty soon it's going to get angry at me over violating 78. Anyway, let's go ahead and run it. And as we can see, the correct rate was 0 here. The sum of all the differences, 400K. Very quickly, it jumps down all the way down to actually after the full 257K steps, although there's quite the gap between 103 and 257 because I went to sleep, we got 100% accuracy. So this model, again, there's 10 billion plausible combinations. The model got 100% accuracy on the out-of-sample testing. No difference, obviously, because of 100% accuracy. So we can definitely train a model to do math. So this was actually really surprising to me to get a perfect score through that. And the other thing we can do is we can actually run the inference. I haven't actually done this, so if we find that it's actually not accurate, I'm going to be pretty angry on video. But let's go ahead and run it. So what's the worst that could go wrong? So this is just running inference.py. Now let's just do like a 5, 6, 7 plus that. I don't even know what the answer should be. Let's pull up the old trusty calculator. Where's the old calculator? So what did we even put in? 5, 6, 7? 5, 6, 7 plus 42, 14, 4781. So the model's top result was 4781. Now, the way this works is it has a thing called the beam width, and that's how many predictions it's going to plausibly make. And then from there, you score them. Basically, this is the model's top choice. But you can see the model was thinking about maybe it's these other things too. But it chose the top result as 4781. That's the one we go with. We could do something super simple. Oh, so this one it actually gets wrong. 5 plus 2, it believed it was 2. 7's actually all the way down here. I'm going to go ahead and guess it's probably not that great at simple math or like small numbers, because I bet small numbers were just like super rare. 40, that should work. Yeah, interesting. So with large ones, it works. What about 500? Well, let's do 5,000 plus 7. Ooh, it gets that one wrong too. This is really interesting that it's getting so many wrong, yet in the sample testing, it got a perfect score. I just wonder if the things that I'm thinking to type in are just so not likely. Let's try it. I'm curious. Does it just never get a single digits right? Oh, it got the 9 right. So this should go over 100,000. Yeah. I don't even know if that's a correct answer. Let's check it. So let's say, actually I can't even tell. I don't know if you guys can see this. Yes, you can. Okay, so that would be 95,421 plus 24,211, 119,632. So it appears to be pretty good at large number addition, but I bet it's just so rare in the training data that it gets small numbers. Let's try 7 plus 100, 7 plus 90. How about 91, blah, blah, blah. So it should be 91, 257. Yeah. So that's interesting. So it's like little numbers that it gets wrong. Let's try 2 digits, 257. Wrong! Did it get 72 in any of the... So none of the outputs did it think 72. So this one has learned addition with large numbers. And that's also wrong. Wow, how did we get 100% accuracy on 500 samples and yet fail so many times through the inference? I wonder if we have a difference in how the inference runs versus... 876, that's right. Huh. I don't know. Maybe because like the same, I don't know. I can only guess why that's acting so much different. It's only for the small numbers though, for the most part. I think we missed one up here too though, right? This one. What about, so this should have been 852. Is that even in? It's got 851. Nah, it's not even in there. Anyway, regardless, probably with more training data and more kind of manipulation, I suspect I could get a model to be perfect. This one was just actually meant to just be a simple test. I never actually intended to even fully train this model, but I was curious. I'm going to go ahead and say this is mostly solved. It's definitely solvable. I think with some tweaking we could get it to be perfect even on the little numbers. But now what I want to talk about is kind of moving forward into the next challenge. So there's kind of two challenges I'd like to consider. One would be just simply doing, so like this was just addition, which is relatively simple, I think. The next task would be something a little more complex, which would be doing all of the symbols. So let me open up math data here. There we go. Open up Sublime, pull this over. So in this case, I've just slightly modified to choose a random choice, both in the training data and the testing data. And then it just chooses add sub, mul, div, one of those. And then what it does is create the training data, and I'll just show you a quick example from N2. I don't know where it went. Here? Yeah. So it's got some subtraction, multiplication, division, addition. It's got all of them, and then obviously all of the answers. So with that, the question becomes, now in this case I think I did 10 million samples. Let me pull it up again real quick. Idle, I'm just so used to it. Yeah, 10 million. So that's the one I'm going to start running right now. Also, even more complex, and I'm going to just probably compare the results in the next video, all in the same video. Also, sample code I'll post. If I forget, I plan to upload the models. So the model that I just showed you guys, just the pure addition, I'm going to upload that model. It shouldn't be too gigantic. Let's see, 20 megabytes. Yeah, so I'll upload that one so you guys can kind of play around with it if you want without having to train it yourselves. And then these ones I'll probably upload if there's anything good about them. But anyways, getting back into these, so I've actually, this one's already started training, and what I'm going to do is I'm going to show you what they look like now. So model, and then we'll come into here. Nope, it's TensorBoard, logdir train underscore lorg. Trainlorg. Perfect. Okay, so this one is just simply one type of number followed by one type of the four plausible operators followed by another number. Again, max 100,000. And what I've got going on here is basically the graph of not only the total. So here, this would be the total difference, right? That total difference that I was showing you before, where it started off as 400,000, that got lower. This is the total difference. And then what I decided was probably smartest was to track the difference of each of these separately. So the difference of the multiplications, right? The multiplications are going to make much grander numbers than, say, division or subtraction, especially subtraction, and plausibly division. Like we can even see division is very, it's already dropping into something reasonable, whereas these are still, you know, at certain exponents. So anyway, so that's how this one's going. I'm only 6,000 steps in, so we still have quite a bit of training to go, but that's how that model's doing. And now I'm going to show you the most complex version and the most complex model that we've got to date. And this one is basically the last step before I start mucking around with doing encryption. So, and by encryption, I mean both trying to either break encryption, but also even just produce encryption. So to actually encrypt things and decrypt things with a neural network rather than some sort of strict rules. Yes, that could go wrong very quickly. Anyway, it's just for fun. So this is a far more complex model. We can see the numbers are much, much higher. What's the difference? So let's bring up the difference. So this one creates much, much more complex mathematical equations. So let me pull up I'm lost. Actually, I think I want to do new data. And then we can check it out. And again, I'll probably post this code. If I forget, someone remind me, because we're running through so many things right now. It's just that if we were to type this all out by hand, one, I'm not sure there's any value to it still, but also it would just take like 10 videos before we could actually just get to the fun part. And this is really just more about having fun. So test 2, let's open that one up. So this is what the results that we're attempting to draw. And I don't know if I can't zoom it with just a plus. But this is what we're coming from. So these are the equations that we're generating. I'll use Atom so I can zoom in. Okay, so as you can see, these are far more complex. It's not just one number and another number. It's many numbers. So one, it's got to learn PEMDAS, right? And then it's also going to have to learn, so not just PEMDAS, like the order of operations without parentheses, but we've also thrown in parentheses to the equations. And as you can see, some of these equations get quite long. So let me also zoom in a little bit. Cool. And so there's a variable number of numbers, there's a variable number of operators and types of operators, and then we've got parentheses and all that. So the question is, can the model learn this? Something like this that's far, far more complex. Now, from what I can tell, again, until we start seeing, like we do see some improvement here, until I start seeing total accuracy doing something, like right now we're missing everything. Until I start seeing accuracy actually ticking up, I'm still a little skeptical that it's not just brute force and it's not just finding similar examples. So we really need to see all of the above. We need to see totals dropping, like the totals of the multiplications dropping. Like these are all differences, by the way. So the difference of output versus desired output, the absolute difference, dropping. Multiplication dropping. Adds is dropping. Subs is dropping. Seems to be leveling out though, unfortunately. But anyway, this is still we haven't even dropped learning rate yet. We're still at the first learning rate. Anyway, I want to see that happening. Of course, I want to see the learning rate continuing to drop down. Let me see if I can pull it up. I think it was probably on that other graph. Actually, not learning rate. I'm sorry. Loss rate. Where is loss? I'm lost. It must be on the second page. Let's try this. Next page, please. There's our loss. Oh, it's super messy. Let's smooth that out. Okay. So actually loss is doing quite well smoothed out anyways. It is dropping still. So anyway, these are the two things you guys have to look forward to. 2 different models are being trained simultaneously, and we will check the results on both of them in the next video. This video is clearly getting way too long. So anyways, I'm going to cut it here. If you have questions, comments, concerns, if I forgot to put up one of these models or we're missing some code or whatever, you want to see the script and it's not in the text-based version of the tutorial, let me know. I'll put it there. If you've got questions, comments, concerns, suggestions for improvement, you feel the desire to support, head to pythonprogramming.net/support. Otherwise, I'll see you in the next tutorials where hopefully we have a model that does these calculations, and then we can go to encryption, taking over the world, that sort of thing. See you next time.